Math 1314, Tyler Junior College, Section 4.5, Exponential Growth and Decay, Logistic Growth Model. There's an inherent problem with exponential growth models. The function that says population's growing and here's what we're going to predict the population is in the future. Recall that the model for exponential growth is A0 times e to the bt. Notice I wrote x by default, but the name of the independent variable is irrelevant. Sometimes it means something though, in this case t means time. If this is a growth model, then the b is greater than 0. Which means that the graph of this function looks something like this. Although there's a horizontal asymptote on the left end of the graph, the right end increases. It will rise forever. I don't care what you're measuring, how big or how small it is. This population cannot go towards infinity. It's going to have to hit some breaking point. If you're measuring population on the planet, as I mentioned in a previous video, there's literally a limit to the size of the population the planet can handle based on the fact that each of us occupy a certain amount of space. So there is a limit to the population. There's a limit to the number of rabbits that can live on the planet or anything else. There's a limit to the number of radiation molecules. Well, radiation doesn't grow, but if it did, there's a limit to the number of radiation molecules that can not only exist on the planet, but in the observable universe. Is the universe infinite? We'll save that for a different class. But assuming that there's a limit to how much anything can grow, then this model, although maybe good in the short term, at some point breaks down and ceases to be reliable. So, how can we fix this? Well, we can look at a different model called a logistic growth model. A growth model is where the rate of growth in a population is proportional to the current size of the population. A logistic growth model also takes into consideration the amount that the population can still grow. So the growth rate is not only proportional to how many people currently exist, but how many more could in the future, assuming some sort of limit. Or think of it this way. Let's say that we have a population of people in a city. And not that this would ever happen, but there's some sort of virus going around that is easy to transmit. If we use what used to be up here, the exponential growth model, to model the number of people in that city that have this virus, at some point it's going to surpass the population of the city. So if there were, say, 50,000 people in a city, and 1,000 of them had the virus, then the other 49,000 doesn't. That's what this is alluding to. The growth rate is proportional to not only how many people in a population are being counted, but how many are not currently being counted. Such a situation, or the function modeling this phenomenon, is called a logistic growth model, and with calculus it can be shown that this model has a particular form. The form of a logistic growth model, first off, is a rational function. The numerator is just a constant, so we'll put c up there. The denominator is 1 plus a times e to the negative bt. The a is positive, the b is positive. Actually, I'm not sure if the a has to be positive. I'm going to strike that out. But I know the b has to be positive. Because by saying the b is positive and sticking a negative on it, then we're guaranteeing that this is a negative coefficient. I guess we could leave off the negative and say b is less than 0, but I'm just being consistent with the reference tool that I'm using right now. And the c is positive, and the c will have to be positive, and here's why. In a logistic growth model, it's impossible for this function, the function's graph, to go up forever, and here's why. In a graph, when you're analyzing end behaviors, particularly the right end behavior, you're asking what happens as x approaches infinity. If If you're unfamiliar with the arrow notation, go watch the video series for section 3.5 rational functions. In other words, what happens, maybe I should have said what happens to f of x. Let me write this larger, especially if you're watching this on a phone. The end of a graph answers the question, what happens to f of x as x approaches infinity, the right end of the graph. For an exponential model, an exponential growth model, the answer is f of x also goes to infinity, but the populations can't go to infinity. Well, what would happen here as the input approaches infinity? In other words, as time goes on, what's going to happen to this function? What is it going to do? It's not going to approach infinity, but I think I can argue and convince you what it is going to approach by looking at the structure of this function. As this t gets larger, we start getting e to a larger and larger negative power. But remember what it means to raise something to a negative power. To raise something to a negative power means the reciprocal of the positive power. So e to the negative bt is the same as 1 over e to the bt. If we incorporated that into the logistic growth function, we would get c over 1 plus a over e to the bt. This is the same function. All I did was write what the negative exponent would do. Now what would happen if the t gets really larger? As the t gets larger, remember we already established that the b was positive. As the t gets larger, the denominator of this little fraction begins to increase. This denominator gets larger and larger and larger. So what does that do to this fraction? In a fraction, as the denominator gets larger, if the numerator is constant, then the fraction collapses down to 0. So in other words, this fraction approaches 0. And now we have c over 1 plus 0, which is c over 1, which is c. So a logistic growth model takes care of the problem with an exponential growth model. A logistic growth model says, as time goes on, your population is going to approach c. That's why in a logistic growth model, the c is what's called the limiting population. It's what I casually alluded to in this setup as the maximum population. So in a city of 50,000 people, the number on top would be 50,000. Let's take a look at a real simple example, and then we'll do one more video that's a little bit more involved. Let's take a look at this one. Suppose in a city of 250,000 people, there's a flu outbreak. Or insert outbreak of your choice. The function f of t equals 250,000 on top, because that's the maximum population of the city, or the current limiting population, if you will, over 1 plus 4,000 e to the negative 1.5 t models the number of people who have contracted the flu T weeks after the initial case. So we got our first flu, start the clock, start counting weeks. How many have the flu after 3 weeks? This question is actually as easy as it sounds. I'm giving you a function and I'm giving you its input. So let's see if this is modeling the spread of flu in the city. How many people would have the flu after 3 weeks. Now, this is assuming that no preventative measures are being taken, meaning that it's just running its natural course. Well, all we have to do is substitute 3 into the function. 250,000 over 1 plus 4,000 e to the negative 1.5 times 3. Word of advice, if you're going to put all this into your calculator at once, anytime you put a large rational expression into a calculator and the numerator or denominator has more than a single number, it's a good idea to put parentheses around that side of the fraction. Because some calculators are not smart enough to know what belongs in a fraction. If you have a calculator that allows you to type a fraction template, then this is pretty easy to put in. But in a calculator that only types from left to right, doesn't have multiple lines, then you have to be a little more savvy. 250,000 divided by, open parentheses, 1 plus 4,000 e to the, my calculator defaults in open parentheses when I press e to the negative 1.5 times 3, close the parentheses on the exponent, close the parentheses on the denominator, and I get a number that's probably larger than you might have been expecting. One person has the flu, start the clock. 3 weeks later, if no preventative measures are taken, according to this model, 5,502 people. Well, that got out of control quickly. If no preventative measures are taken. Gee, I wonder how long it would take for half the population to get the flu if no preventative measures are taken. That sounds like a good question to answer in the next video.